Full screen. Full screen. This is a PDF. Maybe download it. Do you want this? Okay, so let me just change it. Present. It's fine. I'll check. Okay. So, good morning, everyone. I'm Bhavya. Today I'll be giving a talk on writing your own programming language in Rust. So, just okay. So, 1 minute. Yeah. Wait, this is visible, right, to everyone? So I'll be giving this talk on writing your own programming language in Rust. So a few things before I start. Maybe anyone have any doubt in the slide or outside it, just ask right away. Okay. Yeah. So we can start. So just a slight background of me. I've been a Python developer for a lot of years now. I developed these two packages. One was Einstein Pi, and one was PyGlo. Was also involved in some research in physics. So kind of programming enthusiast and have interest in theoretical physics. With Einstein Pi only, I got into Rust. Basically, we were developing this kind of a module which was computation intensive, and we were searching for alternatives to Python actually. And C, C++ seemed quite far coming from Python background. We wanted some middle kind ground to take there. And so Rust seems a good option. We didn't implemented it, but I got into Rust from this project. Yeah, I also recently completed my 50K lines of Rust code. And so I'm past that point where everything for everything I'll be using RC and have started using and arguing about lifetimes and so on. So everywhere in the code, I have these kind of lifetime annotations and not just RC and refcell kind of. Yeah. So hey, you may ask probably why to even write a programming language in first place. We have a lot of programming languages. Rust is one of them, which is doing great actually. So why to write your own programming language? So the most of the these kind of question is not new, and actually the most answered thing is domain specific language. It's not just always you have to write a general purpose programming language. It's mostly you have some, let's say, log files, or you have some configs you want to manage, and you don't want to write some particular code, or you have to call those libraries again and again. So what you can do is you can just define of your own syntax actually, and just write a small DSL for that. And so the compiler construction is basically, if you don't bother about code generation and so on, is basically writing a parser for your syntax and then doing some background tasks depending on how you are interpreting that syntax. So it's mostly that. So mostly when you write your own programming language, it's mostly domain specific language. If you don't want to like work for high level languages and so on, there are people like Zig and even Rust was developed by individuals who are interested in developing higher programming languages, high level programming. So DSL, there are quite a lot of examples of DSL. There are databases. All the database querying languages comes under DSL. There are APIs, GraphQL, typesetting in which these slides have been written. The LaTeX is a DSL. Scientific computing has MATLAB and so on. This last one is YAC, which is basically parser generator, yet another compiler. This is again has a DSL. So yeah, so
But the whole thought that you can actually write a compiler is not a compiler.
Yeah. Yeah, it was interesting. Yeah, correct. Absolutely right. Yeah. Now another question can be why to write a compiler in Rust actually. Okay. So one interesting thing is that Rust itself is written in Rust. Okay. So if you check the GitHub repo, it's 96.7% Rust. So the Rust compiler itself is written in Rust. It's self-hosted. I'll talk more about in later slides. But basically the thing is that the first project they did in Rust was Rust. So it was a compiler. And so Rust is very matured in that terms that you can really write a mature programming like Rust in Rust actually. Okay. Uh, okay, the first version, and then they self-hosted in bootstrap. Yeah, I'll talk about self-hosting in later slides. Yeah. Also, one of the reason is I'll also talk about this. This is the new buzzword, WebAssembly. So it's also one of the targets it can be compiled to, which is WebAssembly, and so you can execute your language in a browser. I'll talk about WebAssembly and how. So not long back there was a time when you cannot execute any language other than JavaScript in browser. But with WebAssembly and with the Rust ecosystem, it's now possible to almost execute any language in Rust in the browser, basically. Okay. And also, I like this code by Rob Pikes that data dominates actually. If you have chosen the right data structures and organize things well, the algorithm will almost be self-evident. And this is even more true in Rust. Well, I really like this thing of enums in Rust, and basically enums have really realized this kind of thought actually, that if you have arranged things which are kind of branching, and most of the time it's branching in enums, it's almost you will never forget to handle those branching cases actually. Okay, so it's like you have shifted if else into a data structure, which is exactly what Rob Pike says. He's one of the co-creators of Golang programming language. Yeah. So Rust has all those kind of ingredients which makes it possible to conveniently write a programming language. You can write it in any language, but it provides you that ecosystem. Okay, I'll talk. So one thing I would basically tell here is that uh, try to go through these slides as kind of identifying buzzwords and not into going into the details. Okay, I won't be going into the details, and mostly it's kind of the buzzwords which you can pick up and then you can take some line and do more findings on that. So the talk will have some terms, but if you have doubt you can ask them, but I would say that you can just skim through it at a high level. Uh, okay, so how a compiler works, basically it's I have taken this TypeScript flow, but it's kind of similar to almost all programming language. You have a lecture, I'll show you in a second in using some concrete example, but you basically compiler is nothing, it's mostly a program which takes a string and then uh, transfers it to some instructions which can be executed in a runtime. Okay, so you just have to interpret a raw string. So TypeScript is a string basically. TypeScript code or Rust code would be a string. It will pass to a lexer. You get some tokens, and basically the major aim of compiler is to make higher and higher abstractions which you can work with. So a raw string is not that good of a data structure to execute basically, right? So then you first tokenize it. I'll show you what tokenization is. Then you parse it, you build an AST is that kind of a data structure which captures the hierarchical nature of code, which then you can do all sorts of crazy analysis like name resolution, type checking, and borrow checking in Rust, let's say, and so on. Once that is done, you just generate the code. There are various strategies to generate code. There can be bytecode generation. There can be compile code, like the assembly code generation, machine code generation. I'll talk about that. But yeah, mostly this is the flow. This is the broader flow, and any compiler you will be constructing would have major modules like this. That there will be a parser module. Even if you see Rust compiler, it will have a parser module, an AST, and so on. Okay. So Lexer basically takes a string and gives out tokens. So tokenization is simply to convert raw code string into list of atomic pieces which can be given to the parser. Basically, again, I said strings is just a collection of characters. You need a much more higher level of data structure to that. So that's what tokens are. Just assume this kind of a simple program. Its tokens would be very intuitive actually. The list of tokens would be something like this. That whole string would be converted to these kind of tokens, list of tokens, which are kind of atomic pieces, indestructible atomic pieces. So first one would be keyword, then we have a space, then identifier, which is the main, then we have L parenthesis, the round parenthesis, then right parenthesis, space, and so on. Okay, you can see it's kind of very self-explanatory. Okay. So once we have this kind of list, this list we give to the parser. Now parser, again, I am telling you that maybe we can skip going into the detail, and just to capture the big idea, basically big idea is that you have these list of tokens, you need a specification, which is the syntax specification kind of your own language. And according to the syntax specification and the tokens, you generate a data structure which we call as abstract syntax tree. An abstract syntax tree, as the name suggests, is a tree which captures the hierarchical nature of the code. So even if without going into much detail, you can see the hierarchical nature. Let's say you have a code. Let's say I'm saying that the whole program is written inside a main function body. Okay. So a code can be represented as fn main, and then in parentheses we have a block. Now what blocks are? Blocks are sequence of statements. Now statements, what are statements? Statements can be statement with a single statement, or it can be a single statement. So you can already kind of getting that idea that it's basically the representation of computer program is hierarchical. It can be recursively expressed like these. Okay. Similarly, variable declaration, let's say, is a statement. Then a statement can be variable declaration, function call, expression, and so on. So every statement, there can be a lot of statements in your language, right? I have taken 4 here. And variable declaration is led, then some identifier, which will be the name of your variable, then equal to, and then an expression. So you can represent the whole syntax, the whole specification of your language like this in recursive symbols. Currently, it's just symbol. It's grammar specification, right? And parser, what parser does is basically it takes into account your specification. It takes into account the tokens, and basically there are different approaches. Mostly the handwritten parsers are recursive descent, and so you can have functions for each non-terminal function, basically, which you can parse. Okay, using the grammar specification. So again, not to go into much detail, it's mostly a linear search actually, by just checking that whether the grammar specification is matched with the statements the code string contains. That's it. Okay. And some backtrack, look up one or two. But yeah, there are approaches which caches the backtrack and gives you an average complexity of O of n only. But yeah, there are some backtracks and so on. But mostly it's linear search. So you wouldn't need a compiler which basically takes more than linear time as your size of code grows. Okay, you don't want that. So most of the algorithms which you will see in compilers are linear in nature. So as your code grows, the time grows linearly.
Sorry, I'm just tempted to ask you. I'm not sure if I'm asking you.
Yeah.
Is this using same?
Is this?
Using same rate?
No, actually, you can use thing. Sync is obviously for procedural macros. If you are doing meta programming in Rust, so obviously you will be using sync there and the parsers and all sorts of things they provide. For here, you can basically, for the language I am writing, I have written, yeah, it's basically you are writing a language in Rust, right? So you would require parser for your language and not the Rust. Sync provides the parser for basically for Rust actually. Okay.
Parser for Rust, or you're using Rust?
I'm using to parse the language. Yeah. Second.
Because sin, the data structures in sin are meant to be interpreted as Rust.
Correct.
It's not interpreting them as Rust.
Right.
To be more accurate, the crate you may not be able to use because that imbibes this grammar.
Mhm.
BCLF form. I
Right,
think
yeah,
it's called.
yeah,
But you can certainly use same data structures for what he's doing. He may not use.
yeah, yeah.
Yeah, but the great
No, it's both things you can use.
No,
The way
the data structures itself are correct.
It's not writing
The sync data structures are bounded to the Rust grammar specifications. Okay. Oh, okay.
I wanted to write a media processing pipeline.
Okay. Ha, ha, ha.
Because I mean, it's not language. It's
Okay.
you add a file reader and a video
Right.
encoder and all.
Yeah.
And it has its syntax,
Mhm.
input, output. So it was for me, it was some sort of a domain specific language.
Okay.
I mean, it doesn't really categorize as that, but
Yeah.
it was some form of notation which I used to pass. I mean, for example,
Mhm.
I was building a media processing pipeline using CLI utility.
Okay, okay.
So I was using Syn to pass that and interpret that, okay, now this is a file
Okay.
reader, like an MP4 file, or then this is a video decoder, and this is a RTP, like network related stuff, like streaming over network and all those elements.
Yes.
So it was, for me, it was some sort of a language,
Okay.
which I was writing on the command line,
Ha, ha, ha.
bash, and it was, and bash was, I mean, you can do auto completion and all of that. And I was using it to auto complete also.
See, obviously, if
There I
you,
was in.
I think in domain specific language, you can take the liberty of the freedom of syntax definition or the freedom to define your own syntax in metaprogramming. I think you can go that far in sync with DSL, but I have to check if you, yeah,
It was not a language.
yeah,
It was not a language. It was
okay,
parsing.
parsing command line, okay. Yeah, again, so just some detailing. So the AST nodes would capture basically this recursive nature. So the variable declaration node will have a let keyword, a name, an equal, and an expression. Okay. Similarly, the expression node can be left expression, the operator plus or something, and the right expression. So again, the data structure itself is capturing that hierarchical nature which you parse basically. Okay. One thing many people should note here is that the AST is capturing the syntax information. It has not yet captured anything related to semantics, that what each symbol would mean, let's say. Okay. So this kind of tree representation you can give, that you have an expression statement and binary. It's very intuitive actually. Mostly the details are kind of obvious. It's I would say more laborious work than kind of non-trivial work. Yeah. So then most of the analysis you do is on this AST, and it's just simple tree traversal, recursive tree traversal. One of the two important passes, AST passes, is one is the name resolution, and another one is type checking if your language is statically typed like Rust or like TypeScript. But you can completely skip this type checking if you are in a language like, let's say, like JavaScript or Python. So Python and all those type checking is done at runtime. The code is running. Okay. Yeah. So name resolution is nothing. It's basically you are catching the declaration nodes in your while you are traversing the AST, and you are inputting it in some kind of hash map. So just a kind which you call as a scope. So very intuitively, if you declare a variable, it goes into the local scope. So the local scope is a hash map kind of thing, and you are just inputting that declaration node. You are collecting the metadata. I'll show you in a second what metadata with each declaration is attached, and then you are just inputting it into the scope hash map. So scope hash map can be basically, you can have nested scopes, and so those will be nested hash maps. Okay, intuitively, very obvious kind of thing. So scope is parent scope, which is I have defined as RC, because it's shared. You can have nested scope. You can have multiple scopes in a global. Yeah. Actually, in the real implementation, I'm even not using RC because again, it has the runtime cost attached with it. It's reference counted. So I'm using index for that. So I have a global flattened out kind of a vector, and I'm storing index to that vector. So it's that pass point where you no more uses RC refcell and uses all sorts of alternative to to avoid runtime cost, or more like an optimizer. The representation is RC. That's why I'm using it. Yeah. So again, I'm saying, I said that we have this hash map, this scope hash map, which is a string, which is the name of the variable or a function or a type, and then you have some symbol data, which is the metadata attached with that variable. Okay. Now symbol data can be function or a variable or a user defined type. Now with variable, you have a variable data, which is the type of that variable. With function data, you have the metadata as parameters, the types of the parameters and the return type. And for struct data, let's say, you have fields and methods. And so for fields, you will have the name of the field and the variable data, which is the data type of the field. And the methods, you will have the name of the method and the function data, which is the parameter data types of the methods and the return type. This kind of metadata you are capturing while processing the declaration nodes. And then we have type checking. Okay. So again, this type checking is in statically typed languages like Rust. So this is kind of all sorts of analysis you do on AST. You can have each pass for it, AST pass. So one was name resolution, another one is type checking. Type checking is kind of captures these kind of whether 1 plus y. Now what is y? First you need to know that. Now name resolution is already done, so you know what y is. Okay. So now it needs to check that 1 plus y is a valid operation or not. Now these kind of checks are not there in Python. So anyone who has done programming in Python knows that this is a runtime error. So your app will crash while giving this error. Okay, and it's not at compile time. In Rust, it won't even let you build that. Okay, so yeah, so these are basically type checking. You can have expression node like 1 plus identified node, which is y, and then with each identified node, because you have done the name resolution, you know what y is. Okay, so y is a variable. From symbol data, you can get that, because the type checking is done at runtime. There are no types actually. There are no type annotations. Everything is object at compile time. The types can be inferred, but obviously we have seen from the experiences of JavaScript and Python that those are not. Yeah, Rust would work here. Python would allow you compiling this thing. Okay. So yeah, so now you can have expression node like this 1 plus y. You know what y is, so you can infer type of 1, which is int, and you can get type of y. You can use the symbol data. So y, let's say, is variable, and with variable you saw that it had the type. So from there you can get the type. You get types of these kind of expressions and variables and identifiers, and then you do type checking. These type checking can be as simple as checking 1 plus y, is it a valid operation, or as complex as the borrow checker in Rust. Okay, so all of this is done in type checking phase. Even if you see the type checker of TypeScript, it's around, I think, 20,000 lines of big code. So all sorts of checks, that whether the fields in the constructors are initialized, that is done in type checking, and all sorts of safeties they are providing basically. Okay. So type checking is a very big module, let's say, in statically typed languages. But the general approach is this, that you just get the type of expression. Will happen in type checker module. It differs with the implementation, but overall, yeah, mostly the module would be type. Right, HRI, and there are lots of yeah. LLVM, yeah. I'll discuss that also. LLVM, yeah. So now once you basically you had the code string, raw code string, you compile, you basically passed it into an AST, you do the checks and so on. Once you are sure that your code does not contain static errors, that this is that again, it depends on the definition. Exactly, yeah. So this is the reason basically. Go is not interpreted. Java is interpreted, but it's JIT compiled.
mean, probably okay.
No, I mean you could claim that it's encrypted because the VM behaves like your CPU.
Right.
in
Yeah.
executing instructions, but really it's already compiled. Now the type checking has been done before the.
No, so it also traces.
For Java.
No, Go is completely compiled. Yeah. There is this history attached to it. Actually, previously there was kind of a basically misuse of the slang interpreted and compiled. Yeah. Actually, the interpreted languages were those which didn't had types, which is not actually correct. Yeah, it's not actually correct. Right. Correct. Yeah. So Java is indeed interpreted if you go by the definition that interpreted languages executes on VM instead of your machine, and compiled languages compiles to assembly language of the instruction set architecture your machine has and executes on real CPU. So that's the kind of dichotomy we are discussing. That's the correct one. Yeah. If you are a compiler guy, then you probably would keep it in Java. Okay. So yeah, again, the compiled languages AST pass generates assembly code. The assembly code is executed on your machine. The interpreted languages generates byte code. Byte code is executed on virtual machine. Now they have best of both worlds, which is the JIT compilation, where you basically compile the byte code into the machine code for hot regions like loops and so on. So that is JIT implementation. It's kind of an optimization, but a good one actually. V8 has proved that previously JavaScript was supposed to be slow, but there are numerous talks talking about JavaScript was supposed to be slow. How the heck they have made it so fast? It's because of JIT actually. Okay, so JIT is kind of JIT is dark art for compiler writers. Just like compiler writing is dark art for backend. Yeah. So it's dark art for compiler writers actually. So yeah. So it's yeah, you have a profiler, you profile the code first, and there is some kind of I would say not just technicality, but you need an art to get it right. And V8 is one of the examples who have done a fantastic job. PyPy also does a pretty good job. Actually, generating a JIT implementation for Python, Google even failed for that. They got Guido van Rossum, who's the creator of Python, to implement JIT, but even he was not able to do that. And PyPy, obviously, they are researchers actually. The people who have implemented PyPy, they have done a great job in JIT implementing that. But mostly you use C Python, which still executes on bytecode. They have this in future projects, but I don't think they will ever implement that. Yeah. So interpreted languages are portable by construction because you are compiling it to bytecode, and to interpret bytecode, you write a VM. So it's from the day one you have that thought in your mind that okay, I'm writing a bytecode interpreted machine, so I have to write VM for that. Okay, and you would be writing VM, and VM are mostly written in languages which are portable. So any machine in which can run your VM can run your language for interpreted languages. Okay, in theory, yeah. But it's not true for compiled languages actually, because compiled languages has to generate assembly for each instruction set which exists there, and so that it can execute on your machine. So instruction set can be x86, ARM, WASM, or RISC-V, or now Apple M1 is there, so it has different instruction sets. So if you want to make your compiled language run on, let's say, Apple M1, you have to compile your language into the assembly of Apple M1. Okay, so it's kind of for each. Apple M1 is RISC is a variation of it's a variation of ARM, but it has a different assembly. It has a different manual. Instruction set is kind of derivative of ARM, but it has a separate assembly manual of that kind of thing. So which seems a daunting task basically. As reference manual for each of these assemblies, if you have ever seen the Intel manual, so around 2000 pages of assembly code and so on. And there are optimizations. People are crazy about optimization, so people have to.
Actually, it is even worse. Not don't think it is worse, but it is even more challenging because even if you simply take the x86, that's just an instruction code.
Correct.
And then there are implementation of that instruction code. For example, Ryzen is an implementation of that
Right.
instruction code, versus Xeon is an implementation of that code. Even within Ryzen and Xeon, every generation will have different set of pipelines and all.
Yes.
So the optimization part for a particular CPU is like
It's
insanely hard.
insanely
Even
hard.
if,
Yeah.
even if it is the same instructions that are being
Correct.
followed.
Yeah.
So that's like another black magic.
Right. And one thing I want to tell here is that mostly if you observe garbage collected languages are interpreted, there is exactly this reason, because interpreted languages has this layer of software, which is the VM. So you can have all sorts of crazy things going during runtime. Okay, because it's executed in your, it's executed on in software basically. The VM is executing, and so you can do all sorts of crazy things, including garbage collection. For compiled languages, that's a daunting task, because you have to attach garbage collecting code, assembly code, inside your compiled code actually. And so they have to insert that. And so mostly you won't see garbage collected compiled languages. Golang has done a great job in that, and I really appreciate those guys that they have really achieved that. I don't remember any language.
They actually implemented pretty much almost an OS inside.
OS, yeah, exactly.
They have 4 rupees, right? Which kind of.
Which, yeah. But yeah, fantastic job they have done, that they have made a compiled languages which is garbage collected, which is really great, because attaching that kind of code which runs on machine, for interpreter you have. So I myself implemented a VM, and implementing garbage collector was not that hard actually, because you have a software layer in which your code is running. But once it's compiled, for compiled languages, it's just assembly. So you have to generate assembly for garbage collection also. So yeah. And so yeah, so compiled languages have this problem of compiling to various architectures, and that's where LLVM IR comes into picture. That LLVM provides an intermediate representation. So they say that, okay, what you do is you compile your language into a global IR, intermediate representation, which we will provide you, which won't change. So any new instruction set would come, it will not change. It's an static IR. And we will take the daunting task of implementing from that IR to all sorts of instruction set architectures like x86, ARM, RISC, MIPS. Now WebAssembly is there, so WebAssembly is another target. So it's the LLVM people who are scratching their head when some Apple launches a new chip. It's not the, let's say, Docker people who are spending day and night. It's the LLVM. Docker people have compiled their software or the Docker to LLVM IR. It's the LLVM guys who are reading those manuals, 2000 pages manuals, and enabling.
I don't think Go compiler is a seven-way.
Go compiler is LLVM.
Golang uses
Yeah, LLVM. It's LLVM. Rust is LLVM. Golang is LLVM. The Clang.
What is which
LLVM was one of the project by Chris Latner, who works in Apple now. So he had this LLVM project as his master's thesis, and then Apple took over, and now it's maintained by Apple.
It's Cornell or some university project.
No, but the major developers are yeah. But yeah. Okay, from that point of view.
It's an independent foundation.
Yeah, it's a project which is sponsored and maintained by all sorts of tech giants.
I think it is Cornell or CMU project originally.
So all the like these manufacturers have to ship LLVM with this?
So now what has happened is that any software which you are creating executable of, the software builders are compiling it to LLVM IR, and then they are using LLVM IR and the infrastructure which LLVM provides to compile it to all sorts of binaries. The reason why you can compile Rust to all sorts of architecture, including WebAssembly, is because of LLVM. Rust guys have just compiled it to LLVM IR. Now it's the power of LLVM that it can compile to all sorts of instruction set architecture, and any new chip comes, LLVM guys are the ones who are spending day and night implementing LLVM IR to that new instruction set target, basically pipeline. Kind of.
Think about it, right? If you are like a processor manufacturer, okay, it is in your best interest to actually have a compiler team that
Yeah.
will make an LLVM IR. So once that is out, you have Rust and everything available.
Correct. Yeah. Yeah.
So yeah, a lot of these people will actually sponsor people who do compiler stuff out of their own personal interest, and that's how LLVM is started.
I'll show you one example from my personal project also. So I wrote this compiler, my own language in Rust, and Rust supports WebAssembly. So I can compile my language to WebAssembly target, and I can execute my own language in browser. No, not exactly. No.
And the second reason is I've seen some what the reason.
Oh, never heard of that. Yeah, yeah. This is surprising actually.
Correct. I saw that. as well.
I think even if they say they are moving away,
I heard about it, yes, but I'm not read why that.
that's really surprising because now every compiled language is using LLVM IR because it has so much perks, right? Yeah, it has.
JVM world is Scala.
Scala compiles to bytecode of Java. Scala, Kotlin. It uses LLVM in its JIT compilation. So JVM uses JIT, right? So JVM is JIT compiled. For JIT compilation, they are using LLVM. Scala and Kotlin are using Java bytecode as their IR. So again, these guys,
Java bytecode is there.
yeah, Java bytecode is their IR. So basically, okay. Okay. Hey, you can do once you know this kind of tech stack, right? You can do all sorts of crazy things. You can compile Python code to binary using LLVM.
So that
Yeah.
is one more thing that I don't know the answer for that. Like, I have seen pretty much compilers for pretty much all languages, but I've never seen a compiler for Python. I don't know why.
Again, this is yeah, maybe so there is JIT, obviously PyPy is doing, but yeah, the compile, yeah,
You write a Python and
Huh.
it converts
It can,
everything to
yeah.
Python. I have seen some effort in that direction, but I don't know why there have not been an implementation of Python.
There is, it's called LPy.
It's there?
Look at
Okay.
this scheme, right? It's like it has high level language.
Huh. Yeah.
Compilers for that.
Yeah.
I don't know why there are no for Python.
Yeah, I have also.
Does it sit on the so we have ship LLVM with along with your compiler or what?
No, LLVM will just generate the executable. So in
Build Rust.
yeah.
You need libclimb. Okay, libclimb. LLVM.
LLVM, yeah. With the compiler itself, LLVM, that whole project would also come, like the executable of LLVM.
To build Rust, you need the LLVM there. But
Yeah.
once you have a Rust compiler, the whatever is required from LLVM is already there.
Right, yeah.
It might also again dynamically be required for some.
Yeah. Again, yeah, the last point is LLVM IR also support WASM target. So LLVM IR compiles to all sorts of instruction sets. They are now supporting WASM also. So you can write your own compiled language and run it in a browser. Let's say, which is which was a far off dream a few years back actually. People cannot think about executing any language other than JavaScript in browser. But now it's possible with WebAssembly.
As WASM in browser is actually compiled to script and which is actually JavaScript.
No, actually they have VM. The browser ships WASM VM itself. Okay. No, now every browser ships along with the JavaScript runtime. They are also shipping WASM VM. So yeah, really, yeah. Because there is WASM runtime, yeah. Just like JavaScript, what they did, they are doing. Yeah. Okay, yeah. During that, ASM did that. Yeah. Oh, at the time of ASM, they did. They compiled it to a stripped down, efficient version of JavaScript. That they were doing. But WASM now browser ship proper, yeah. It's not yet garbage collector, so the runtime does not. It's not. This traces back to the reason why Rust is interesting actually with WASM. WASM VM doesn't support garbage collection as of now. And so Rust being a language which is not garbage collector is really good target for WASM because it's really efficient. For Python, if you want to run them inside browser, you have to compile the whole C Python into WASM binary, and then that executes on. So it's like your VM is executed on a VM. Correct. Exactly. Yeah. Yeah. Go does. Go does. Actually, as I told you, Go is compiled garbage collector. So the garbage collected code also they have attached. But the thing is that WASM VM does not support garbage collection. So in Go also they have that kind of. Not overhead. It's the whole VM of your language which is running on WASM, which you don't get. Yeah. Very small. Yeah. So
everything is practically you don't have anything there. Yeah, because everything is inside the
right. So you are kind of, just to give you an idea, you are sending the whole interpreter down the wire to the user's browser, let's say. If you want to execute it in all browser environment. No.
Python is not exactly same for Python and Rust.
No. See, WASM is an instruction.
Python.
Huh. Okay. Yeah.
And similar functionality in Rust. It also runs in
Yeah.
compared to .Python.
Right.
But these are not same.
No, not same. Exactly. So you are sending the whole interpreter down the wire. Yeah. See, that's the problem. I'm developing the. So basically, it would be slow boot time, but the advantages you are getting when you are running it in browser. People have developed 3D graphical games with WASM. The boot time is obviously slow. Huh. Right. Correct. Yeah.
And they moved it to like browser because of WASM. And in fact, one of the interesting examples, which is where this thing has started was long back there was Google Earth, right? And Google Earth had like this natural light.
Yeah.
In C++, they used to like make it, but just to make it happen for browsers, like these.
Yeah. AutoCAD, Figma, Adobe, all these are examples. They are shifting to browser. Yeah. Which again was a far off dream. If you see the era of static web pages, there at that time no one can say that I'll be running a game actually. Huh. That's true. But even the
completely down to the wire. So
yeah.
So the browser is downloading the web assembly.
Yeah.
So let's understand bytecode or WAT.
Yeah.
The WAT format. So that means there is something that is interpreting the actual format or bytecode and.
No. So you will compile your whole interpreter, the Python interpreter, C Python in WASM, and you will send this binary to the exactly. So your VM is running on WASM VM, and which is executing your code. So it doesn't make sense actually to send interpreted languages. Now there is this Google assembly which is coming into picture, which is saying that they will start using JavaScript garbage collector inside WASM VM also. So now this will solve the problem. They will just send the Python bytecode would be compiled to WASM, let's say, and that binary itself would be going, which will just contain your code, and that code can execute on WASM VM. Given now we have support for garbage collection, the only problem we are facing is that garbage collection is not supported in WASM VM.
No, but then the information has to also go there.
Correct. Yeah.
From a garbage collector.
Right. Yeah. But that information mostly it's runtime information. Actually, that the profiler JavaScript profiler would be profiling that what all heap objects are active in memory, what to clean, and so on. But yeah, there would be some metadata which will be sent in the binary, in the Python binary. But yeah, Google is working. They have a very matured WebAssembly team there, which is working with enabling garbage collection for WASM VM also. So the LLVM infrastructure has this very famous web page, which is my first language front end with LLVM tutorial. Now it's just front end you have to write. You just have to write your syntax, grammar specification, and compile it to LLVM IR. You can have a compiled language, your own compiled language, which is as fast as C or C++, if you don't have a lot of complications, or if you are developing a simple language. LLVM provides you that. It even does the optimizations on LLVM IR itself. So all sorts of 1 level, 2 level, 3 level optimizations which you study in compiler course or so on can be done on LLVM IR itself. Yeah, another one buzzword is transpilers, which if you are coming from web development world, you would have heard that we have JavaScript transpilers and so on, like TypeScript. So transpilers are nothing but they are just compiling the language into some high level language. Like TypeScript is doing it for JavaScript. So their IR is JavaScript only. Okay. So it's nothing fancy there. Actually, it's just they are compiling. Basically, TypeScript have to just remove the type annotation. Okay, and just remove constructs like interfaces and generics and so on. They just remove it. You get the JavaScript code, then you can just execute. So the runtime they are borrowing from JavaScript only. So TypeScript does not have a runtime.
Let's consider AWS Lambda.
Yeah.
Ship a code, right?
Right.
Behind the scene, you can even go for optical that you cannot always look, because they can transfer the code, what is written into their past.
Right. Correct. Yeah. See, again, you can do all sorts of crazy things if you have this front end in place. Actually, just the parser and the AST and all the analysis. If you have those things in place, you can do. There are a lot of matured infrastructure which you can use to like make a very efficient programming language. Like Zig is one of those examples. The guy who has written Zig, Andrew Kelly, who use LLVM IR, and that's why Zig is really fast. Obviously, they must have been using some language specific optimizations, but mostly it's LLVM which is providing the speed of compiled languages.
What problem does Zig solve?
Zig removes some basically.
Okay, you might want to go ahead. Let me put it this way.
Mhm.
I mean, why not? It's probably not solving any problem, but they're probably doing it just, but it is more like a typeface C than
Correct.
actually something closer to Rust.
It's nowhere near to Rust. Obviously, it's not providing any safety
But
guarantees.
something like typeface C.
It's modern C. You can say that anyone who wants to use the modern
Yeah, it is.
Yeah. No, in that sense, Rust is kind of revolutionary. Yeah. Rust. Yeah. Rust is it. Yeah. Like, correct. Yeah.
I think no language gives you that satisfaction that it compiles, and if you have not used any unsafe,
Yeah. Yeah. This kind of going back to Python, I was so scared to write code in Python. There are no types. I don't even know whether the type checking is there, because it will crash in runtime. So Rust kind of spoils you in that area, but it's really revolutionary in that sense that they have.
And not have the issue where he is talking and you're people. So we'll take whatever finish, we'll take a small break.
Okay. Sure. So how much time?
Take your time, but
I'll just complete it. It's on the end. Yeah. When I was writing, actually, I was thinking that maybe we can skip some slides. I would, yeah. So transpilers are those. Then self-hosted compilers. There are a lot of examples. Now there is this saying in compiler world that if your language is not self-hosted, then who would use it basically? That if you are not implementing your language in your own language, then who would? So TypeScript is 98.8% TypeScript. Okay. Zig is 95.9. Golang is 88.3. How self? Huh? Rust is almost 100%. I would say. Rust I showed not 99. Yeah.
That small point there was that X.5.
I think yes. So how self-hosting works is basically, let's say you want to write a Go compiler. Now you already have a Go compiler, right? I can write a Go compiler in Go. What a compiler is, compiler takes a string and transforms it to executable instruction. You can choose to write that kind of software in Go, and you can take that string as Go code, and you can do that. So that's how self-hosting works. Basically, if you have written a version 1 in some other language, you have a working language. Now you can use that language to write code of the compiler, which can take code string of your own language and compile it. So it's pretty straightforward, actually, self-hosting. There are various approaches to self-hosting. Zig is one of those who got into the pitfall of one of the approaches, which mostly not many people uses, actually. So this versioning based self-hosting only mostly is used by Go or Rust.
It is called self-hosting, but used to be before the
Okay.
Shaders.
Uh-huh.
Shader is actually you back to the program.
Okay.
TLS with the-
Okay.
Send the screen to the like it happens in runtime.
Okay. Uh-huh. Okay. Yeah, basically it's like kind of flavor of meta programming that you are providing. Yeah. Another one is language server protocol. Again, this is compiler as a service. Basically, instead of having command line compilation, your compiler is active in memory running as a server, and your client is communicating with it. So all these ID support you get in TypeScript and Rust and so on are language server protocol implementations. That your compiler, it is basically in every click, your ID or the editor is sending request to the language server, and it is making some changes in the semantic analysis we talked about. So it has an active AST inside a memory. There is a lot of tricks and art they do, basically because your code is broken. When you're writing your code, it's broken, and traditionally broken code cannot be parsed, but they are even parsing it and making a partial AST inside. So that's the kind. Even the compiler which I wrote is able to make partial AST. It's kind of an art, but once you read from articles of Microsoft and so on, they have defined a very neat approach. They have written I think PHP error tolerant parser for that. So maybe if you want, I can share that article. So it explains that approach, which is now taken.
VS Code popularized this a lot.
Right. The Microsoft has a very matured compiler group with Roslyn, .NET, TypeScript, C#. They have very matured team for that. WebAssembly we have already discussed. Again, this we have discussed. Rust is awesome for WebAssembly because WebAssembly VM as of now does not support garbage collection. And for Python, it sends the whole interpreted. So Pyodite is one of the standards for basically having Python code executed on browser, and they are doing this only, they have compiled the whole thing. Where you can start learning about these things. So crafting, yeah. So don't pick up Dragon Book if anyone knows. Yeah.
That's insane.
Yeah. I even working on compiler for 1.5 years, I don't have the courage to touch that book. Basically, the initial chapters are fine, but there are more modern approaches to write compiler from an implementation point of view that contains a lot of theory. And so this book is really absolute. It will take you all the way from zero code to building a interpreted garbage collected language, a matured garbage collected language having classes, object orientation, and all sorts of things. It's a nice book. If you go from cover to cover, you will have your own programming language. And it's a nice project to implement it in Rust, because Rust would pose some difficulties while you will be following that book. So it's nice to, yeah. Any questions? Okay, yeah, then I think.
But you have not given any demo of the language.
Yeah, so I have to get my laptop. Yeah.
You can give the demo, just keep it here so that recording can happen.
Okay. Okay. So this is the playground of the language. The name is Jarville. It's not open source.
Already made a playground.
Yeah. So I wanted to experiment with WebAssembly and that kind of, and so yeah. So this would look like Python because there are no types actually, but you can start adding types. Again, to solve the problem of Python, you need separation between declaration and assignment. Python has everything in just one syntax. So you define let x and let y equals to true. Then you can have kind of start running this. It will give you type check. Now we need to compile. We need to run this code. But once the language server implementation is done, we can just show red in the ID itself as you type that x plus y, just like Rust ID does it. So you can do.
This is all in Rust, right?
Yeah. So again, I wanted to basically tell that Rust is matured in that sense also. This I'm using a Rust crate to print this pretty error diagnostics. So it's really nice from that end actually. Yeah, so language has classes. It has lambdas. You can have type. It has basic types like int, bool, or string, and you can have
Pretty amazing.
struct. String coming from Rust. If you define in now again, one pain point in Python was that you have to throw self in every method. So I just removed that. Why to pass if you can enable it in the
you
scope?
do the static method and class method.
Yeah, that's the problem. So the compiler automatically detects whether the method is using self. So if it's not using self, it's a class method. So you have to have class dot.
Achha, so you will actually do the analysis of the code.
Yeah, in type checking, everything is. I'll show that also. So if you.
This is pretty cool, man.
Yeah. So let's say if you just print something like name.
Yeah, so this becomes a class method.
So this will say that field's name is not initialized inside the constructor. Okay, so it will.
So it actually knows that
Yeah.
it is a constructor.
Correct. It knows it's a constructor. It knows that every field should be initialized, because if it's not initialized inside the constructor, it's kind of a bug. Initialize it with any value, but you have to initialize.
Okay, so here the name is self.name or just name?
It's just name. Now I'll use self.name to initialize it. Self. Now if I so basic type checking, that false has type bool. Self.name is string. Now I'll just have it name. So okay, let's remove this error. So I have two types of comments. You can have Rust-like comments also. So it compiles. Then you can.
Okay. I have a couple of questions. So it also knows that underscore init is a special kind of a method, right?
Yeah.
I mean, I call simply. Let's say I simply call it as init. Okay.
Yeah.
You can do that. Just say def init.
Uh-huh.
Or you have to define a
Def init.
Name str whatever you want.
Okay.
And then print name should print x should be fine, right? What doesn't matter.
Okay.
Print x should be fine here, right?
Print name.
Sorry,
Yeah.
should be fine here.
Yeah.
So it understands that init underscore init is some
Is a special function.
Wow.
You can use self.name inside this.
Then it becomes.
No, it's a class method because you are using self. Now, not a method.
So it's a method. It's not a class method.
You can build the object. Yeah. So it says that expected one parameter, got nothing. So you just provide anything like Rust. Okay. So it prints that because the init method had print. You can call object.init. You can pass any string. Let's say I can just change.
Doesn't matter, right? It's not exactly.
Name. Now, if you do this, let's say if I'm using some print self.name inside it, it's fine. It will print. But if you're not using any self in the method, so then it will give error because no method is there. So now you're there node.
Node.
Right.
Just like
not
node in it.
Just see, the thing is that language is not that mature, so there can be bugs also, right? Okay. Yeah. And this is demonstration. So the rule of demonstration is that anything Node,
use
yeah,
that.
yeah, sure. Yeah, there are lambdas.
Amazing, man. I love
Yeah.
this.
You can have lambda checking also. Lambda checking is structural. So let's say you have, let's say, some get handler kind of method, which is x int, and then you return a handler type. So you have multi-line lambdas. In Python, you just have single line lambda. So let x func is equals to, you define lambda like, let's say, y bool, okay, and x int like this, and then you can just print x, let's say, and then you return func. So it will say that expected return value was handler, but you provided a lambda which has a functional type which is int and x. So now what you can just attach a string basically,
String, and then return
and return anything. So now, yeah. So this is the type checking. It's a closure. So basically, you can close stuff inside that. So let's say if this was x, right? Let's change it x. So you can print x. So it's kind of capturing the closed variable. It is written in the string. And so now we can have let func equals to object dot get. Again, this doesn't, okay, then just print self name only.
Is it tab strict or you can move the print to right hand?
It's that, yeah, just like Python, it has intended that thing. So int anything 12
and then call
func. If you call directly this thing, it will say that func expected two parameters because it expects int and boolean. So you provide it. So yeah, so it has printed at the end also Rust is. So it also has generics. I can show you generics, but it's kind of, it's in work in progress. So anything can go wrong. But you can have this kind of syntax like node. If you have, you can have t, and then you can define interface. It will give you error generic type arguments expected by the type. I have not provided here.
I
So
wanted to ask about generics. So मैंने सोचा कि यार वो एक इतने साल लगे generics.
no, so that I was familiar with the experience of Go and thought that it's hard.
First class from day
Yeah, it's hard, but I'll implement it from day one. So it's bounded generics are there. It's not that it's in work in progress. Everything is done in on paper, but only the laborious work is basically remaining. But yeah, everything is done actually. You can define an interface. I have a local code which does that. So it has this kind of generics and interfaces and so.
It's pretty cool, man. Really cool.
Not yet. On 3-4 months, I'm waiting to complete generics only because generics are that.
People will check and nothing will work.
Yeah.
How does it matter?
One problem is that I am still sending the whole interpreter down the wire in Playground. That is very slow. The boot up time is very slow. So the official,
Fine, man. I mean,
yeah, I think.
that's pretty good. Man. Amazing.
How much time have you taken to?
1.5 years.
Yeah, it takes time.
It takes.
Part of it is to learn.
Actually, the main aim to write this was maybe I'll
Present state.
Yeah, so yeah,
ठीक है, I'll do the rest.
we'll do the rest, right? Can you get started? Okay. So let me just what do I mean by that, right? A lot of times when we see some code, right, you already see it in a end product form. You generally don't get to see how you have actually got there. A lot of times we make mistakes, but you don't get to see the mistakes the programmer has written. Okay, so a very common example of that is you will see something like arg mutex something. You don't know why the hell somebody wrote it like that. Okay, even though you have read arg, what arg is for, what mutex is for. So what I tried to do, and this is something I didn't prepare for the talk. This is something I had gone through myself. So the idea here is, let us try to solve a simple problem. A simple problem is there is going to be a hash map which you want to update from 2 threads. Okay. Now hash map is just an example. It could be any shared state which you want to update from two threads. Okay. And how do we actually go about doing that problem? Okay. So I encourage you to follow along. I think Rust Playground would work just fine if you are using Rust Playground. Otherwise, if you have a Rust installation on Linux, it's awesome. Okay. So somewhere we read in the Rust book that you can use Arc to actually share data in multiple threads, and you can update using some data from multiple threads. So let us first. What I'm going to do is I'm not going to type everything in the interest of time. Okay. I'm just going to copy and explain all the code. Okay. So first let us start with a simple example that there is a hash map. Okay, so what we are going to do is we have a hash map, a simple hash map where the keys are integer 32 and values are string. Nothing fancy, no references and all, something very simple. And we want to actually update this hash map from 2 different threads. Okay, so we go and we actually go and read the documentation.
But
yeah, go ahead.
But that should be in a mutex, the hash map.
Yeah, but how do you know we will come to that. Exactly, because first off, when you start writing a program, you don't know you have to use a mutex. So you will come to know why we have to use a mutex. Okay, so we go and look up the manual of Arc and we find there is something somewhere there is a get mute. So I think we can use get mute and try to do a get mute on that, and we should be able to we should be able to update the hash map in the hash map from 2 to. So if we run it, I think so.
So you are able to do without type. Type inference. This is very difficult, but.
Sorry, because I remember now. We'll see.
Collections.
No, I think it's just a steady thread.
I think collections.
Okay, so what we are trying to do is we are trying to update this hash map, one from a thread that we had just spawned here in this, and one outside the thread, and basically nothing gets updated. So we wonder why, what happens. So what happens is if you actually go and look again, hash map get mute, right? It returns an option Okay, and it returns a null value if the arc contains if the underlying story is shared by more than one thread. Okay, so which means whenever you are trying to actually update this hash map, you are always going to get a none and you cannot update, because that kind of makes sense, because this is how you avoid data races in Rust. But we do want to do that. So what do we do next? Okay, so maybe what is happening here? Let us try to look at this code. Okay, so this join handle is actually a handle to a thread that has been spawned. So this join handle lives all the way up to this point till you are joining here and dropping it. And since at this point there is a join handle as well as the outside map, both of them are active. The reference count is more than 1, and you cannot. That's why you are getting none. So maybe what we can do is, what if we join this first? We may be able to do it. Okay. Okay, so what we were able to do, okay, it's not visible here. What we are able to do is, we are not still able to update the hash map inside the spawn thread, because up until this point, right? Up until this point, both the spawn thread and the main thread are active. Okay, so you are still going to get a none. Okay, and but after here, at this point, this join handle is not going to be used anymore. And since you have joined it, you are going to get an option value which is going to be some value, and you will be able to update it. Okay, so okay, we are at least able to update it from one thread, but ideally we want to update it from both the threads. Okay, so we need to do something. Now actually comes the problem of now we need to do something more. Simply using arc and hash map is not going to be enough. So what do we do? So there is a type in Rust called as mutex, which offers you something called as interior mutability. What do you mean by that? So as we have seen already, that you cannot have two mutable references to something at the same time, right? But you still probably need, in some cases, you would need to update something from the two, contexts of execution, either threads or whatever. So how do you do that? So what does a mutex do? Okay, if we read a little bit about mutex.
I have a small doubt.
Yeah, sure. Go ahead.
In this example, it could be so happen that instead of word, it could be also hello. Like let's say.
No, it will not happen. Why? This will definitely not happen. I'll tell you why. Because till you join, right? You're always going to get a
Main thread.
no. You're always going to get a none, because that arc is shared.
Okay.
See, this thread has to go out of scope. Yeah, I mean, this thread has to end first. Only then you could get it.
But this thread ends after let equal to
The join handle, right?
Yeah.
So now, up until this point, right? Okay, I got your question. What you are saying? Well, you should get a hello here.
Hello as well. I mean, it depends on the execution.
No, because you are joining here, right? So you are actually blocking here. So it doesn't depend on the execution. You will be blocking here.
It will be waiting there.
Yeah, it will be waiting there.
See, the thing is, you already took, there was a mutable reference, right? You already cloned it even before the thread was formed. So,
So exactly. Oh, that's the point. So this is a clone, right?
Yeah.
So even before this thread is spawned, this is already cloned. So the reference count is 2 already. Since the reference count is 2, here it tries to see the reference count is 2.
Correct.
I cannot get an exclusive access to this, so it returns a null. You cannot do anything. Now when it is dropped here, the reference count is dropped to 1, and now you can actually use this arcmap clone and you can go ahead. Got it? It doesn't depend. I mean, yes, we will take an example of a race condition also. Okay. But it doesn't depend upon, it will always be world, because up to this point, the arc was always cloned.
Okay.
After this point, the arc is, I mean, one of the clones got dropped. So you will get an exclusive handle to an arc. Okay.
Just one observation.
Yeah.
That, so spawning a thread
Yeah.
and then joining on the thread does not mean the compiler will still think that the thread can outlive the main function, right?
Yes, it can. The compiler will, yeah, I mean, it will assume that it can have
There is
a.
a thread scope. That's why.
No, I didn't get what do you mean by
So,
thread scope.
so what I'm saying is, so you take there's a data which you have declared,
Yeah.
and that data you're mutating in another thread, and you're joining on the thread in your main function. I mean, the compiler can still say that the thread can outlive the main function. I mean, the compiler will not look at.
Okay, so compiler is trying to be conservative here. Let's put it this way.
Okay.
I mean,
That's because thread has something called as thread scope, STD thread scope, where you
Yeah.
say that the thread, by the time it reaches that line, join handles or join.
Yeah.
If it was that thread was spawned within a scope, then there is a guarantee for the compiler that is over.
yeah, but here the scope is the entire function, right?
Correct, yeah. What I'm saying,
Yeah, but to actually answer your question.
Join there, I know, I mean, because you're taking step by step. So basically, merely having a join there does not mean that for the compiler is happy that the thread will cease to exist at that point.
Two ways to look at it. At least right now, the way it is happening is it's very conservative. Okay, I cannot think of a scenario where compiler can actually reasonably reason out that okay, the thread is not living beyond this point. I didn't to get me. I cannot.
No, what I'm saying, let's not talk about arc. What I'm saying is I have a main function.
Yeah.
This is my question. I'm not like implying maybe I could be wrong. So what I'm saying, if I have a main function and I have declared a variable, and after that I've created a thread.
And you're moving that variable to the thread.
No, it's a mutable variable, and I'm mutating that variable in that thread.
In the thread.
Not moving. It's basically referencing the thread. Okay. But I'm joining. That code will not compile, right?
That code will not compile.
Correct.
Yeah.
Because the compiler will not say that.
But yes, the code will not compile. But actually, if you see, it is still conservative.
Correct.
I mean, if the compiler could reason out, right?
Exactly. That's what I'm saying.
That you are joining here, the code does not exist.
It
That does not happen today.
For that, you have to put it in STD thread scope and then spawn the thread within the scope.
So I have not used thread scope. Yeah, that is one. Or some other data compiler would want to be able to reason out, okay, the thread does not exist beyond this point. Why not?
Yeah. For that, there's something called as thread scope, and inside a thread scope.
Okay, I have not
used
used that.
scope variable, and then on that scope you do scope.spawn,
Okay.
which will guarantee that when that scope ends.
Okay. So here you cannot guarantee because this is still conservative. I mean, there is nothing that stops from an implementation of a compiler to actually allow this as well. Okay. So now we know that okay, in order to actually update data from two threads, we need to use something called as a mutex because mutex allows you to have an exclusive access to a particular data structure. Okay. So we'll just copy this. Never mind. Okay, so what we are now doing is let me just. So this is where things start getting really interesting. So what we are doing, we know that okay, we have to use some kind of a mutex to actually be able to update from this. So mutex implements something called as an interior mutability. What does that mean? So if you think about it, right, you cannot just get a mutable reference to, you cannot get two mutable reference to anything in Rust. So what mutex does is if you get this, so what do you do in mutex is you actually call a function called as a lock, which actually returns what is called as a mutex guard. And the mutex guard lives only up to the current scope in which it is defined. Okay. So now here, this particular code knows that I have an exclusive access to the code. Okay. And then it can actually do a deref mute of whatever you have got. Okay, it implements a deref mute, and that's why you can actually get a mute on this, and you can still insert. Okay, so in theory, this should work. Okay, there is a bit of a problem here. Okay, and this problem is little interesting. What happens is, what happens is you have taken a clone of this. Now, if you take a lock, right? Before this outside map goes out of scope, okay, this lock is not going to get exited, and then as a result of which, this particular lock is going to this particular lock is going to get blocked. Okay, so you are going to see a deadlock in this code because you have to, because this particular lock, this particular mutex guard which is written by this particular lock is still in scope, and it is still not going out of scope. Okay, and you are going to see a deadlock. So we will try to see. So we are seeing here we see a deadlock because the spawn thread is never able to get the access to lock. For that to happen, the mutex guard which was there in the main thread has to go out of the scope, which never happened, right? So actually this is a deadlock. It is not guaranteed to happen that this deadlock will always come, but in pretty much almost always this will happen because you are already in a main thread, and spawning another thread OS is going to take some finite amount of time, and you are already in the main thread. So that's why you will see the deadlock. But if thread 1 somehow magically was spawned before you actually get to a point where you are getting the mutex, right? You could still be able to update this, right? So one way of doing this is the simple stupid way of doing it, delay the execution of main thread. Okay, so we can see that okay, we will probably be able to get rid of that deadlock. If we actually call the current thread to sleep for some time. What is the duration? STD duration?
STD time.
Time duration.
But then the thread will take the mutex guard for that.
Yeah, so thread will take the mutex guard, but it will exit because the thread is over after taking the mutex guard. So the mutex guard is over because the function is exiting. Correct. So that thread is gone. Correct. Now you come to a main thread. Up to that point, main thread was blocking. Correct. Now, but it gets the lock again and it is able to update again. Okay, see, but this type of code is a problem, right? Oh, sorry. This type of code is actually a problem because you don't know how much time you are supposed to wait. And this is generally not a very good idea to actually synchronize between threads by randomly sleeping in a thread. Okay, so is there a better way of actually doing that? Okay, as it turns out, there is a better way of doing that. What was the problem here, right? We got a mutex guard that didn't go out of scope. Okay, and because of that, one thread was actually blocking. What if we somehow make that mutex guard go out of scope? Immediately, right? So if we just put a scope around that particular part where you are getting the mutex guard, we should be fine. Okay, that is exactly what the final solution for this looks like.
So inside the thread you will put the scope?
No.
In the main function.
In the main function, you put a scope, so that you make the mutex are lived only for a small scope. Okay. Or I can just pass that to I can do that in some function. That just becomes the life of that function becomes a scope. Right? See, if you see what we are here, we are actually doing is we are creating a block, okay, making sure that this mutex guard gets dropped here, okay. Now this somewhere at this point, this thread is going to get unblocked. You will get a reference to this as well, and then you are joining in this. So here there is no some random thread where sleeping and all of that, right? So this is probably like the cleanest way of updating something from multiple threads. I don't know.
You have to take the sleep.
See, now we are able to run it from without doing some random weights and all. Okay. So this was one simple example of. So finally, now what you will typically see, right? You will typically see any code if you are any code that is written, you will directly see it in this form. Okay, not in this form. This is something else. Wait a minute. You will see it in this form, and you have no idea how somebody actually arrived at this particular implementation without actually making mistakes. So we were actually trying to imitate the kind of mistakes that we would typically make when we are trying to write a code. Write a code that looks like. So this is going to be the final form. Okay. Now, if you there's one more thing that we are going to look at is if you actually see a lot of people say like, yes, this is one demonstration of how you can actually change the shared state from two different variables. From two different types of context. Okay. In general, even if you can do something like that, in general, in any real world code, that's not such a good idea. Why? Because something that gets changed into unrelated execution context, it becomes very difficult to reason about, okay, where something might be getting changed. Okay, again, this is fine for small programs in few files, but if your program becomes very big, this becomes a bit of a problem because it becomes very difficult to reason about that code. Okay, so what is a way? What is a way to actually solve this problem? Okay, so people who come from the Go world would have heard about channels and things like that, right? It seems that it's also possible to do something very similar in Rust. Okay, we'll take a look at an example. So what you do is all the mutations to even a shared data structure, so-called shared data structure, always happen in a single thread or a single context of execution. Okay, and whenever someone else wants to make a change to a given structure, that someone is just going to send a change to this thread to actually go and change. This is a pattern that was first made famous by Erlang. Okay, 35 years ago, maybe a little more, 40 years ago, 30 years ago. This is a pattern that is being used by the Go and Go routines and everywhere, and a lot of modern so-called actor frameworks and all use this pattern where modifications to a state is localized, happens in the same context, and you basically modify that state through message passing. Okay, so we will actually see an example where we don't even have to use an arc because arc is ultimately still a shared data structure. Okay, so the way we will go about it is I have just Okay, so let us talk a little bit about this. So we kind of got how we came up to the arc and mutex and all part, right? So it seems that we can actually do that even without ever using any arc or any of that form. Okay, so the way to do about that is go about doing that is something called as channels. Okay, so how many of you have programmed in Go? Pretty much a lot of you, and in Rust, some of you at least. Okay, so you know what channels are. So we will use something very similar like channels. Okay, and actually do this so that we don't have to mutate the state in the 2-1. So for example, if you really look at it, just looks little verbose, okay, but let us try to actually understand what it is, okay. And this is also for the first time I am also introducing a couple of concepts in Rust like type enums and all. If you are not used to it, this might become little too much, but bear with me. So what we are really going to be doing here, right? So we have an enum called a channel data. What that enum is, it's going to come in two variants. One is going to be a real data that you want to actually, and then another is some kind of a signal which says that, okay, this is an end of file or this is terminal or whatever, which says that I'm done sending data. Okay, so that is the idea of that. Now it turns, since it's a first class type in Rust, you can send this first class type in Rust across threads also. Sorry, across channels. I don't want to use the word thread as it. Okay, you can use this across channels since it's a first class type. There are restrictions, like it has to be sent because you want to be able to send it across this. So anything inside an enum has to be sent. But I mean, something this simple, that should be fine. Okay. Now, how do we? So the channels in Rust are multi-producer, single consumer. We are just going to be using the single producer and a single consumer. What does multi-producer, single consumer means is more than one thread can actually write to a channel, but only one can consume. Here we are only going to be using one single producer, but that's more like a function of what code we are writing rather than the limitation of the channel per se. So here what we are doing is we create a channel, okay, and since Rust cannot simply, if we did something like this simply, right? Rust cannot infer what data you are going to be sending on channel, right? So it cannot do type inference and tell, okay, this is the data I'm going to be sending on channel, and probably looking at some next code it might be able to do, but it becomes very difficult. So you have to be a little explicit about the type of the stuff that you are going to be sending on the channel. Okay.
Can you do the types on, like, is it another API for doing it on channel side so we can ignore the sender receiver state?
No, I didn't get it.
I mean, it's just a syntactic thing question, but instead of the channel data being the type here,
yeah, you can do it on the right hand side.
maybe just once on the right hand side.
You can do something like this.
Yeah, turbo.
Something like this. I don't know what is the exact syntax. Probably something like this. Something like this.
No, after channel.
No, I don't think, because that is a data type. Let us try.
Yeah, something like this. Okay. And
Let
then
us
would you
try.
do
The test of the pies to eat it. This should also work.
No, if that's a bother, we just wanted to check if that's.
No, but without actually having that, we won't know whether this is compiling. Type are even not allowed, so you have to give an explicit one.
I was expecting the type argument on the channel rather than as part of your namespace.
No. This is not a min. Oh, okay.
Yeah, channel data is your own custom.
MPSC is a module name. Sorry, I'm so
Yeah,
sorry. Sorry.
Yeah.
Sorry, my problem. My bad. Yeah, this works too. So you're just telling it what kind of channel. So you don't have to be. But the key point here is without actually giving the data type that is going to be sent across the channel, the compiler cannot do a type inference. Okay. And let us look at this a little bit more. Okay. So what here, if you observe, we are not using any arc anymore, right? We are just simply using a hash map. Okay. And then we are moving this hash map to this particular thread. We could as well have done something like this. That's fine too. But and let us look at what we are doing in a main thread. Okay, in a main thread, what we are doing is we are basically running an infinite loop and trying to see what data comes on the channel, right? And whenever a data is received on a channel, it has got a result type. If I'm not wrong, it has got a result type. So if it has got a result type, we will see which variant of the enum it is. If it is an EOF variant, we are going to say, okay, we are done with receiving data. We don't need to be doing anything. We will just exit the infinite loop. What might happen is that the sender is closed. Now, if the sender is closed on a channel, the receive function is going to receive an error. Now, when you receive an error, it also means that every sender who was supposed to be sending is done sending on the channel. So we will be exiting that channel also. So if you really look at it, this is what we are trying to do here. Okay, and this is something called as pattern matching. Okay, this is another beautiful feature of Rust that you can write code like this trivially, and once you get used to it, you pretty much don't know other way of writing code. Okay. So what we are saying is, if whatever is received on a channel, if it is an OK type of a result, okay, and then we will see whether it's because we know that if it is an OK type of result, that means it's an enum, because that is how the channel was defined. If that is an enum, then we will see whether it is the first variant, which is the valid data, or if it's an EOF. If it's an EOF, we are done receiving, so we will exit it. If it is a valid data, we will be going to be doing map.insert.
So, okay. You have defined EOF there, so I thought EOF is always important.
No, EOF is just a variant. It's not an int. It has like no type as such. And, or I could have simply not used this and have some special value of int -1 or minus less than 0 as EOF, something like that also. But this is far better convention to use than simply saying that positive integers are valid, and I32 I have only used for this. Okay, and here now we are not showing it, but you can just see that we can actually send the data on a channel and update it in a thread. So this is still achieving what we wanted to achieve, that some state was to be updated from two different threads or from the two different execution contexts. And one execution context simply says, okay, simply passes a message, and then the other execution context simply updates it. Okay, what are the advantages of doing this, right? Why do you like to do that? Now, if you use something like an arc, right, the example that we saw, there are chances of actually creating deadlocks, okay, because if the code is really big, it's very hard to reason about. That is number one. Even if you don't create deadlocks, arcs still are expensive. Arc and mutexes are still expensive because, especially in a massively parallel system, because they make use of an atomic variable, and if you actually try to go a little deeper into what an atomic variable does, whenever you update an atomic variable, the processor has to actually broadcast through something called as cache coherence protocols to all other processors that this particular variable or memory location is getting updated, and that's an expensive operation, usually taking several cycles. Okay, so that's why the message passing is so fast in multiprocessor system, because you don't get this cache coherence protocol overheads, because you are not pretty much using anything atomic. Atomics are good places where you have to use it for because there is no other way. That's good. But generally, if you can avoid that, it's even better, because this is all happening on single thread. So you get all the cache benefits, all of that. So that's why you are. It's not guaranteed that you can just never have to use ARC or something like that. But as far as possible, avoid any shared mutations to data, even though the language provides you with that kind of facility. Okay.
Just to add there, right? Like when we
just use channels, we are actually kind of using the language abstraction.
Language, exactly.
Everything which is like there. So it internally uses something called as a concern for software transactional memory. Right? What it does basically is it kind of linearizes the even though there are multiple threads that are accessing, it kind of linearizes them or serializes them. As if
Yes.
happening in a transaction.
It might itself be using atomic values itself. I'm not denying that.
Communicating sequential process or something like that.
Yeah,
But-
CSP. That's what Go does.
Yeah.
What is that? I didn't know.
Communicating sequential process, right? Like that's a term, or even STM, we call it as software transaction.
So and this is something that.
Actors use the CSP and Go things and they use STM.
Okay, I don't know the exact details of implementation of channel. Oh, we didn't have that. Yeah. And you will see here the sender drop because the thread. Oh, sorry. If you actually see here, you will see the sender drop printed because what happens is if you look at it at this point of time, because once it is done sending, it is going to drop the sender. So what this is going to receive an error value on the result, and it will print the sender drop, and that's why it breaks. Or you could actually explicitly do something like and then you can still exit out of the loop without actually the sender dropping. Okay, so but let's see, you'll probably not. Yeah, you didn't see the sender drop right now because you actually received. You broke out even before the sender was dropped. So that was the main idea that generally when you see a code in its end result form, you don't know how you actually arrived at it. And these are like some of the experiments through which you could actually understand what is happening, and then you are now. I mean, for example, whenever I saw arc mutex something, I had no clue why the hell a mutex has to be kept in an arc or something like that. Now, trying out something like this gives a better understanding. Okay, this is why people are using that. You don't always have to use mutex. If you can use atomic variables, that's still fine too. But not.
If you don't, I mean, again, hypothetically, I'm saying, you can still use mutex without putting it in R, provided that you know what it is. I mean,
Provided you-
compiler will compile the code.
Yeah, see, it is not that the mutex has to be kept inside an arc. Okay, but almost rarely you would use it.
Yeah, for example, if I'm not using arc, and if I'm just because I think mutex is one data structure in Rust that that has sync, right? Basically, that you can share the reference of
Yeah.
it across threads.
No, mutex reference of it you cannot share.
No, I mean mutex implements the trait called as sync.
Mutex implements sync? I don't think so. I don't think so. I could be wrong, but I don't think so. Logically, it doesn't make sense.
No, I'm not sure. Yeah, I thought.
Yeah,
it implements-
logically, I mean, again, I have to.
RC does not implement both, but I think mutex implements sync. And send also.
Maybe.
RC does not implement send. Mutex implements.
RC does not implement both items.
You cannot. Yeah.
But I think mutex implements sync, right? It has to be but T has to be sent. Mutex over T has to be sent. But,
T has to be sent.
but mutex in itself can be sync.
Mutex,
I mean,
yeah, you can have a shared.
You
Yeah,
can open the documentation.
yeah, it could be makes sense. Mutex can be sync. Yes, you can get a shared reference to mutex into.
Yeah, so that way you can use it across threads, provided that mutex does not outlive.
Yeah.
The left side is the trait implementations.
Yeah, it implements
Auto trait,
send.
blanket trait or auto trait, something like that.
No, it implements. It implements both send and sync as well. So you can pass mutex across threads.
Yeah,
But T has to be a send.
T has to be a send.
T has to be a.
I think The left, you can just scroll down, the left column which is there.
I think we were seeing on this part of this mainly.
Yeah.
Send and sync.
Yeah, this is for the mutex. No, but what about the T?
You can click on sync, I think, and then open the source.
No, here there is no restriction on T as well.
Can you click on the source?
Source, yeah. I mean, our source will be little painful. I mean, it will do so much of indirection.
Yeah, no idea. So there is no, yeah, T can be.
Okay, it uses some unsafe thing. I have to see. I mean, this is something I always get confused.
No T, yeah, so there is no restriction.
But I'm wondering why.
No, mutex has to be synced, right? Because it's like.
It has to be synced, yeah.
Yes.
But that means you can take anything and send it across channel if you wrap it inside a mutex, which kind of seems very odd because there is no restriction on T.
But I think mutex does not implement copy, so it will move to that thread. Mutex itself will move to that thread, right? So if I'm saying I'm just sending the mutex across a channel or to the different thread using move, then it will just, I mean, it won't make a copy. It will just set the entire mutex will go ahead. So you will not be able to use mutex only.
Mutex on the from where you send, from where you send.
I think so. I'm not sure.
No, it could be. I don't. Copy is unlikely. I mean, copy to yeah, it doesn't use copy. Copy to वो नहीं करेगा. But I thought there should be some restrictions on T, which is kind of odd. Let me.
What is mutex guard? I think you can look at mutex guard because I think
mutex guard does not implement sync.
Because it has to not implement sync.
It cannot implement sync. Otherwise, the whole point is.
But it says it's implementing sync.
Is it?
Yes. On the trade.
So the T has to be sync.
T has to be sync.
What is sync trade, by the way?
I have
So sync is sync means you can send the reference
across a channel or to another thread.
To a different thread, right? The reference can be used
Like send is
send is like you're sending the
actual data.
Implements a copy, you make a copy and send. Or if a team implements does not implement a copy, but that's a new and just so there's a RCA of the reference count can be sent across, cannot be sent across the thread.
And R does can be sent.
Can I switch it off? Can I stop sharing?
Move or add works. Move or different thread works.
Lead Studio, is it? Stop screen, huh?